Hello everyone and welcome back to the next episode. In this episode we're finally gonna implement our collision detection for polygons versus circles, and then we finally implemented everything we need for the collision detection step. Alright, then let's jump right into this. In the collision detection JS file, we have to implement actually 3 new methods. The first method is going to be static circle versus polygon edges. And here we have the shape circle and the shape polygon. Okay, then we have another method, and this is going to be the circle versus polygon corners method. Alright, and here we have again the shape of the circle and the shape of the polygon. Alright, and then we have a new method, and this is on a really top one, because this will be the method we're gonna do our collision checks now, and this will be the static check collisions method. I made a small mistake here. There we go. And this will be the shape A and shape B. And I'm first gonna implement this method. Here we're gonna decide which method we need to call. Like if we need to call the circle versus circle, if we need to call polygon versus polygon, or if we need to call the circle versus polygon method. But first I'm gonna create a variable called collision manifold, set it to null. And then I'm gonna check if the first case, if shape A is an instance of circle and shape B is an instance of circle, then, well, of course, we need to check for circle versus circle. So I'm going to call the circle versus circle method here. This will be shape A and shape B. Then we can have another case, and this is the polygon versus polygon case. So we need to check if shape A is an instance of a polygon, and if shape B is an instance of a polygon, then of course we need to call the polygon versus polygon method. So again, shape A and shape B. All right, and then we have the last case, and this is the shape A instance of circle and shape B instance of polygon, I mean, of course, yeah. And that's it. And I'm just set an else. Well, actually, I don't need an else here. And we also do not really need here the else if, but sorry. Well, no, never mind. But yeah, actually, yeah, we can just say this one. This will, I think it will work too, but I'm just gonna make sure that this will be the right case in any case. So that's why I'm gonna say it like this, and I say of course, circle versus polygon. Nope, that's the circle versus polygon. And here I'm going to say again shape A and shape B. All right. Did I declare this method already? I think so, right? Yeah. No, I didn't. Ah, of course. Okay, yeah, we have to add 4 methods actually. So I need to add the circle versus polygon too. And here we're gonna call either circle versus polygon edges. Well, we're gonna, yeah, or the circle versus polygon corner method. Why did I call it like this? Okay, that's better. Yeah, and here we need to set shape A and shape B again. Okay. Good. And I think that's it. Of course, we need to return the collision manifold. Already forgot that already again. Collision manifold. All right, so let me check if that's right. That looks good so far. All right. All right, cool. Now we can implement the circle versus polygon method. And the circle versus polygon method, in this method, I'm again declaring some variables. This is going to be shape circle, will be shape A. Just going to rename the variables now. And shape polygon is shape B. Of course, you also can change these parameters here to that name, but I'm just going to do it like this. And then we get a contact point. First, we check for circle versus edges. So shape circle and then shape polygon. And here, if the contact is null, no, actually, if there is a contact, then we're gonna return that contact. Because if there's no contact in this method, this means, well, either the circle is not touching the edge, there's no contact, probably the circle is not touching the edge, or the circle is in an invalid area where we need to check for the circle versus polygon corners. And here we're gonna do that now. This will be just a else. Here I'm gonna return this dot circle versus polygon corners. Shape circle and again shape polygon. Okay. That looks good, I think. Yes, it does, I think. Yeah, I mean, I'm gonna run into an error when I try it anyways. But yeah, just let us finish everything and then we can do some debug here. Okay, now to the interesting part, circle versus polygon edges. We're gonna do this one first. And here we are going to define some variables. And the first one will be the vertices length. So from the shape polygon. So shape polygon, vertices length, then the circle centroid is the shape circle centroid, then the nearest edge vertex. I will set this one to null. Also the nearest edge normal, set it to null. And then we have to now iterate through every vertice and do our checks I showed you in the last episode. So add a for loop I to 0, then smaller than vertices length, I plus plus. All right. Then I'm gonna declare another, some more methods, and I mean variables. This will be the current vertex. That's the shape polygon. Oh no, shape polygon, vertices, the element at the index. Then the current normal. This is the shape polygon normals. Then we have the next vertice, or the next vertex. I'm gonna call it here vertex. Is shape polygon dot vertices. Yeah, and here I'm gonna use the math helper function with the index method. I'm gonna say I plus 1 vertices length. So it's to avoid the index out of bounds things. That's why I'm gonna use it here again. And now we're gonna create the direction vector to the circle from the current vertex to the circle. So the vert to circle is the subtraction from the circle centroid with the current vertex. Okay, then we have the dir to next. This is the direction vector from the current vertex to the next vertex. We need that too. And we need the length of this direction vector. And if we have the length and this direction vector, then we can do our checks if the circle is in the right area. Okay, so the direction vector is the subtraction from the next vertex. Yeah, it's the subtraction from the current minus the, I mean, the next vertex minus the current vertex. That's the direction vector. Then the length of this one, dir to next length, is the dir to next dot length, and then the dir to next normalize. Okay, here we can normalize. Well, here we will normalize the thing, and then we can do a projection with this direction. Then we get the projected value, and then we can compare. If that value is less than 0, then it's an invalid area. If the value is larger than the length of this direction vector, then it's also an invalid value. And if it's in between those two, then that's an right one, and then we can check for penetration. Actually, if this value, if the circle center is in the right area, then we're gonna set these two variables, okay? And there's only one case where we need, or when we need to set these things. There's no other way. We don't need to iterate through and compare values like we did with the polygons. Like, you know, where we set a penetration depth and then set a penetration depth again and compare these things. We don't need to do it here. There's just one case. We just need to find like really the nearest edge vertex. And yeah, there will be no other case here. We don't need to compare anything else with values. That's the cool thing about this method. Yeah, but we're gonna do the penetration calculation in a later step after the for loop. Okay, now I think we can do the projection. So I'm gonna declare another variable. This will be cycle dir to next projection. This is equal to vertice circle, vertice to circle, and the dot product from the dir to next. Note this dir to next, the direction vector from the vertice 1, vertice 0 to the vertice 1 is now normalized. We're gonna do the dot product with the normalized direction vector. This one is not normalized, so we get a projection value, and we can compare this projection value with yeah if it's smaller than 0 and greater than the length. Okay, so let's add that. Circle due to normal projection. Oh no, that's the other one. We're gonna do that later. Circle due to next projection. Yeah, this is the one. If that's greater than 0, then we have well, that's one condition we have to meet if the circle is in our area. And if the circle there to next projection is smaller than the to next length. Okay, so if it's greater than 0 and if it's smaller than the length of the direction vector, then it is in our valid area. And then we can set the nearest edge normal to the curve normal and the nearest edge vertex to the curve vertex. All right. Right, and now we're gonna add one last step, and this step will ensure that there's just one possible solution to this, and we don't need to cycle and compare values. And this is the circle direction to normal projection. This is the vertex to circle, the dot product with the current normal. And here we check if the circle projection to normal projection, a really funky name, is greater or equal to 0. This makes sure that the circle center is not inside the polygon. And it will make sure that there's only one possible solution. The problem with this is, of course, if there's a large case of tunneling, then we might have a problem and the circle will stuck inside the polygon. That's not a really good solution to this problem, but it simplifies the whole collision detection. And also our shapes will be large enough, and our circles will be large enough that tunneling will not be a problem in this scenario. Also, the circles, it's gonna be anyways a problem if the tunneling is that big of a problem, then you need to use a other collision detection method, or use the same one, but like how's it called? Continuous collision detection and continuous dynamic, I think it's called, where you will do a raycast and check for collisions then. And I think that's well, it's not a really good solution, but I think it's good enough for our physics engine. If the circles are too fast, then we can also just we can also use, or we also should use then continuous collision detection to avoid tunneling. Yeah, but you need to use it anyways when the circles are that fast. All right, so I think it's okay to do it like this. If you don't have any plan or any idea what I'm talking about, it's not a problem. Continuous collision detection might be a topic for a bonus episode at the very end of the tutorial series. So don't worry what I'm talking about, just add this one here too. Or you can also just leave it and see what happens. And then add it again and yeah, see what happens again, right? And what fixes it. Okay. So now we can make a check. Oops. Again, after the for loop, we say if the nearest edge normal is still null, and the nearest edge normal is still null. Well, actually, I changed it to an or, because if I don't think there's a case that this one can be null, but just to make sure, if one of those is null, just return null, because then there's no collision. Okay. Yeah, and here this is the case. If the circle is in an invalid area, then we're going to return null because we didn't find the nearest edge, or an valid edge. You can also say that's a valid edge normal, for example. But if there is something, then we have to calculate the penetration, and this is the vertex to circle, a new variable, subtraction from the circle centroid with the nearest edge vertex. So it's again a direction vector with the nearest edge vertex. Then we're going to do a projection. Projection to edge normal is equal to nearest edge normal dot with the vertex to circle. Here we're going to see if the circle is actually colliding with the edge, alright? And here I'm going to say if the projection edge to normal minus, like in the slides I did, minus the shape circle radius, alright? Did I say get radius? I'm not sure anymore. I think I can just say the radius. Should work. Is smaller than 0. Then we have a penetration, alright? And then we can calculate that penetration depth. And this is, well, it's pretty much the same actually. So we can just copy this one. That's the penetration depth. Then we have the penetration point. And here, like in the presentation I did, here we need to add to the circle centroid a direction vector. And the direction vector is, well, the nearest edge normal, right? The nearest edge normal scaled by the radius, right? So let's do that. Scale nearest edge normal and shape circle radius. But this is now flipped. It's in the wrong direction. So I need to say -1. Okay, then we have the penetration point. And now we can finally return the collision manifold. So return new collision manifold, penetration point, the penetration. Note the penetration depth is, in my case, in the wrong direction. So I'm gonna, well, it's negative. I need to have a positive penetration depth. Also depends on your implementation. So you need to check if you have that a little bit different. And also the nearest edge normals in the other direction. So I need to scale it also to with -1. And then I can say penetration point. Okay. And if there's still no collision, then we say return null. All right, and this is our circle versus polygon edges method. Quite a big one, but I hope it's a bit more understandable than the polygon versus polygon method. Okay, and now for the last one, the circle versus polygon corners. In this method, we say, well, actually, I will do it in the next episode because this episode is already quite long, 25 minutes. And we also need to do some debugging too, and change in the do some change in the simulation class. So I think that this episode will be a bit too long then. Yeah, I'm gonna do that in the next episode, and yeah, see you then. Have a nice day, and I hope it was a bit clear. If not, just watch it again. I guess it's the best option. Yeah. All right. Then see you in the next one, and bye bye.